Welcome everyone, I'm Matt with That Programmer Guy, and I'm here to talk about bitwise operators. We'll cover what they are, how they work, and some of the ways to use them, so let's get into it. Bitwise operators work on several ones and zeros at once instead of individual bits. This is different from Boolean values where developers work on each true, false, or 1, 0 individual. However, the fact that bitwise operators work on multiple bits is where you get their power. You have 6 main categories of bitwise operations. You have your AND, OR, XOR, sometimes called exclusive OR, NOT, left shift, and right shift. And the right shift operator has 2 main variants. We'll cover what these operators are and some of the ways they can be used through your code. So the first operator we'll cover is AND. AND takes 2 inputs, A and B, and it returns a single output. For every bit in A and B, we will check if both are 1. If they are both 1, then we put a 1 in the output. If either bit is 0, then we put a 0 in the output. We do this for every bit in both A and B. The next operator is OR, which is similar in that it takes 2 inputs and does 1 output, but it operates a little differently. With OR, we will do a 1 in the output if either inputs have a 1 in that bit. So here we have 2 ones in the first bit, so we get a 1 in the output, and then we have a 0 and a 1, so we get a 1 in the output. And we will only get a 0 in the output if both inputs are 0. XOR is our next one, and this is sometimes called the exclusive OR, since it will only put a 1 in the output if exactly one input has a 1. If both inputs have a 1, then you get a 0. So we can go through this again. We get a 0 for the first bit, and then we get a 1, 1, and then a 0 for the last. We have the NOT operator. What the NOT operator does is it will change 0 bits to 1 bits and 1 bits to 0 bits. So we can use this to invert a binary value. Up next is left shift. And a left shift operator takes a shift amount as one input and the binary values to shift as the second. So this isn't 2 binary inputs, this is a number input and a binary input. And what we do is for every bit in the input, we will go to the output and count the shift amount of bits over. So in this case, we're going to go over to the left 3 spots, and then we're going to put that 1 there. And then we're going to do this for all of our bits until we fill our array. Once we fill out our output, the leftover bits are discarded, and then we fill in that gap at the start with zeros. Before we get to the right shift operator, we do need to talk a little bit about how integers are represented in binary, just so that we can understand why there's 2 variants for a right shift. In binary, we can have signed integers, and these integers can be positive or negative. And it is the first bit, or the signed bit, that represents whether or not it is a positive number or a negative number. Negative numbers have a 1 in this position, positive numbers have a 0 in this position. When we do a right shift, we are taking that topmost bit and shifting it over to the right. If we were to always fill in with zeros, then negative numbers would become positive after doing a right shift. Because we sometimes want to preserve the sign of the number being shifted, we have 2 variants. We have a signed right shift and an unsigned right shift. A signed right shift will preserve the sign of the number, whereas an unsigned right shift will lose the sign information of the number. So we'll cover both of these variants at once, since they're very similar all the way up until the last step where we fill in the number. Similar to a left shift, we're going to take a binary number and we're going to take the bits, we're going to copy them to the output but shift it over. We're going to start with the bit on the left rather than the bit on the right this time. And we're going to shift it over to the right 2 places. We're going to do this for all of our different bits until we've copied over everything, and then we're going to drop the last 2 bits. For our unsigned shift, we're going to fill in the start with zeros all the time. For our signed shift, we're going to look at that first bit and then copy that over to the output. In this case, our first bit is 1, so the entire gap will be filled with 1s. We can do the same thing with a positive number which has a 0 in the first bit. We copy all the bits over, we then drop the last 2 bits, copy a 0, and then we look at that sign bit, which is a 0, so we copy zeros over, and then we are done. Now we're going to start getting into some of the use cases for these bitwise operators. We've seen how they work. We haven't seen how to use them together to do something useful. The first thing we're going to look at is compacting a bunch of Boolean values into a single representation called a flag. Booleans represent a single true false value. That is one bit of information. Bools, however, are often stored in an integer behind the scenes, which is usually about 32 bits. Sometimes a programming language may have an optimization to compress an array of Boolean values to a single byte per Boolean, but that's not always a guarantee. And even then, sometimes it's implementation specific. So if you switch your runtime, it may no longer happen. What flags do is they take all of these Boolean values and compress them into a single integer, and it uses individual bits to set and retrieve each Boolean value. And this means that if you have 5 different Boolean values, instead of taking 20 bytes of memory to represent them all as separate integers, you could use a single byte to represent all 5 values. You'll often find this in video or graphics libraries as well as in embedded systems. Differentiates uppercase letters and lowercase letters. By toggling that one bit, you can change the case of a letter. Do keep in mind this only applies to ASCII letters. You don't want to be applying this operation to non-ASCII letters. The bit is represented in hexadecimal as 20. Down below, I have an uppercase A and a lowercase a, and I've bolded the one bit that is different between them. So now let's dive into code that does case operations on ASCII characters. So at the first, we have a helper method isLetter. We're using this to restrict changes to only be on letters. We don't want to be trying to change the case on a number or on a control character because that can cause unintended side effects. We also have a constant for our case bit. That way we don't have to have this 0x20 throughout our code. We just know this is the bit that determines the case for a letter, and we can just reuse that. Up next is our lowercase method. What this does is it iterates over all the characters of a string, and if it is a letter, it will set the case bit using an OR operator. Similarly, we have the uppercase method, and this will clear the bit using a combination of the AND operator and the NOT operator. And then finally, we have toggle case, and this will use an XOR operator to toggle the case of our letters. And here we have a main method, and this is using our helper methods above to change the case of some text. So now we can compile our ASCII C file, and we can run it, and we can see that it is working. We are getting our original text, we're toggling the case of all the letters, and then we're lowercasing everything and uppercasing everything. So thank you for watching. If you found this video helpful, please like and subscribe, and I'll see you next time.